Okay, so yesterday we are discussing the effect of the troposphere. We noted that the troposphere is a non-dispersive medium, meaning both code and carrier are affected the same way while traveling to the troposphere, and in fact both of them slow down. They travel at a speed less than the speed of light in a vacuum. And then since the medium is non-dispersive, the error does not depend on the carrier frequency, unlike the ionosphere. As a result, we cannot use the dual frequency measurements to remove the tropospheric error. Next, let's quickly find the tropospheric error. Now, since both code and carrier slow down while traveling through the troposphere, we also call it tropospheric delay. In case of the ionosphere, the code is slowed down and the carrier is advanced. So, the ionospheric error for the code is also called the ionospheric delay. Why delay? Because if the code slows down, it will reach late, right? The time of reception will be more. That's why the error is actually the effect of the error is delaying things, right? That's why we call it delay. Okay, but since the carrier is advanced while traveling through the ionosphere, we do not call it call the ionospheric error ionospheric delay in case of the carrier. An equivalent description would be ionospheric advance, but we do not use that term. We just use ionospheric error for the carrier. Whereas for the code, we can call it the ionospheric delay as well. Okay. In case of the troposphere, both are slowed down, so we can say the tropospheric delay because the error is positive basically here. Now this has two components. Okay. Delay due to dry gases and then delay due to water vapor. This is also called wet delay. Now to find the expression of the tropospheric delay, we will introduce a term called refractivity. So we know the refractive index. Refractive index that is C by V. Right? Next we introduce another term called refractivity. As n minus 1 into 10 to the power 6. Okay, this is a convention. Okay, and the refractivity has two components. One is due to the dry component, another is due to the wet component. So this is for dry and this is for wet. Okay, now using the refractivity, we are going to find the expression for the tropospheric delay, and we will adopt the same approach as before. So we need to find the delta T tropo. What is delta T tropo? Delta T tropo is the actual travel time of the signal in the troposphere and the travel time that we would have got if had there been no troposphere. Let me see what notation I used for that. T prime. Here we do not need code or carrier separately because the time would be the same for both. So this is the travel time had there been no atmosphere. If the signal had traveled through a vacuum along the entire path, and then this is the travel time to the troposphere. So this one is the same way. dl by v, and then we need to substitute for v. This one is so delta T tropo is actually 1 by C this one we are going to replace with n. We know that n minus 1 into 10 to the power 6 is capital N refractivity. So n minus 1 would be n into 10 to the power minus 6. We'll replace this one. And then substitute for n as nd plus n weight, and then separating these two we get so the first term is actually the delay due to dry gases, and the second one is delay due to weight component, due to the water vapor. Okay. Now, since there is no way we can remove the tropospheric delay using the dual frequency measurements, we need to use mathematical models to remove the delay to the extent possible. The tropospheric delay, delta T tropo, depends on pressure, temperature, and humidity. Okay. The dry component can be modeled easily. But the weight component is hard to model. So the weight component shows more variability. Okay, so they depend more. The weight component depends more on these meteorological parameters and shows greater variability. The more the variability, the more difficult it is to model. Different models that the user can use are I'll just give the names. We will not discuss them in detail. So these are some of the models that the GNSS user can use to partially correct the tropospheric delay. Okay. So that's all about the troposphere. We'll conclude this topic with a comparison of the two layers of the atmosphere as far as GNSS is concerned. So we have ionosphere and troposphere. And we are going to compare their effects with respect to some features. The first one is variability. Variability is high in case of the ionosphere because it depends on so many factors. So it can have diurnal variation, seasonal variation. It also depends on solar activities. And then there could be a variation depending on latitude and longitude as well. On the other hand, the troposphere has comparatively low variability due to meteorological parameters, due to the weight component, which depends mainly on the meteorological parameters. The next one is the delay, or the order of the delay in meters. So we have delta t, and if we multiply the speed of light in a vacuum, we'll get the delay in meters. Okay, so it is not difficult to convert seconds to meters. You just multiply the speed of light in a vacuum, and you will get the delay in meters. In fact, if you recall the pseudo-range measurement equation, there you multiply c to delta t. So we are interested in the delay in meters. In case of the ionosphere, it is several meters to tens of meters. Okay, it also depends on the elevation angle. The lower the elevation angle, the higher is the error, because the signal has to travel a longer path. Then in case of the troposphere, it is on the order of 2 to 4 meters at sea level. Again, it depends on elevation angles. Now, modeling error. We know that for single frequency measurements, the user has to use a mathematical model to partially remove the ionosphere. We discussed this yesterday. In case of the troposphere, we have no option but to use a model to partially remove the tropospheric error. So what is the order of the modeling error? In case of the ionosphere, it is in the meter level. Okay. Whereas in case of the troposphere, it is in the centimeter level. Without meteorological parameters. So you can use some default values of the parameters in the model and get this delay. Then this would give more error. But in case of the troposphere, the error is in the centimeter level for high elevation satellites. Okay, for low elevation, again the error is small. And then the next and the last feature is how they behave with respect to the radio frequency. We discussed that the ionosphere is a dispersive medium. Whereas the troposphere is non-dispersive. So in case of the ionosphere, the refractive index depends on the radio frequency, carrier frequency. Whereas in case of the troposphere, the refractive index does not depend on the carrier frequency. It does not change from one frequency to another. That's why the troposphere is non-dispersive and the ionosphere is dispersive. Okay. So this completes the discussion of the ionosphere and troposphere. Um, if you have any question, you can ask me. Otherwise, I will move on to the next topic and the final topic, which is GNSS receiver operating principles. And there will certainly be questions on this. Whatever we are discussing, and we will discuss. There will certainly be questions, and it is also difficult to understand. I have already given you the book chapters that you can read, but if you do not understand things in class, you will not be able to follow the book chapters also. Okay. We'll discuss the final topic using PPT, and I have noted the major points on the slides, but it is not possible for me to note everything on slides, so I am going to give explanations orally, and you need to jot down the main points. Not every point is captured here. There are things that I will be saying orally, and either you need to jot down the main points that you will not find here, or uh, you need to go through the recording again. So first we'll have a brief overview of different receiver primary blocks. Then following this, we will look at each of the primary blocks in little more detail. The first two blocks that we'll discuss are the reference oscillators. The receiver has a clock, the reference which we call the reference oscillators, and then GNSS antennas. Okay. So we know that a GNSS receiver is a user equipment that receives signals from the satellites and processes the signals to obtain the user position, velocity, and time. By time, we mean the receiver clock error from GNSS system time. So by correcting the clock, it is possible to derive the GNSS system time using an inexpensive clock. There are basically 6 primary components of a receiver GNSS antenna. Okay, this is the block diagram that shows all the primary components of a receiver. So this is the GNSS antenna, which is followed by front end. I'll quickly tell you what each of these does. So do not worry about the terms now. And then the front end is followed by baseband signal processor. The next component after the baseband signal processor is the ranging processor, and then the final one is the navigation processor. Now all these blocks, the front end, the baseband signal processor, ranging processor, and navigation processor, they are driven by the receiver clock. Okay. The receiver clock has a reference oscillator that generates either sinusoidal signal or a square wave at a particular frequency. But different blocks actually have different requirements. For example, here you require a frequency at the gigahertz level, here you require at megahertz level, here you may require at the fraction of a second. So it's not possible to have different reference oscillators. To generate different frequency signals as required by different blocks, there is a synthesizer whose job is basically to derive different frequency signals from the reference oscillator. Okay. GNSS antenna receives signals from the satellites in the form of electromagnetic waves, and then its job is to convert the electromagnetic waves into electrical signals. Because we cannot process electromagnetic waves, we need to convert the electromagnetic waves into electrical signals for further processing. Okay. Now at this point, signals are basically analog electrical signals. And then the receiver part I already discussed on the previous slide. So it has a reference oscillator followed by a synthesizer which generates different frequency signals, reference signals for different blocks. Then the electrical signals, analog electrical signals from the antenna go to the next block called the front end. See, when the signals are transmitted by satellites, the signals have limited power. It's not possible by satellites to pump in a lot of power, because a lot of power requires heavy equipment, more resources, which cannot be done on board the satellite. So generally, the power that is pumped into the transmitted signal would be on the order of few tens of watt. For example, in case of GPS, it is on the order of 27 watt. Now, the signal travels a long distance from satellite to the user, because satellites are thousands of kilometers away. In case of GPS, 20,000 to about 26,000 kilometers for a receiver on the surface of the Earth. In case of IRNSS, it is even more, about 36,000 kilometers. So the signal travels a long distance from satellite. Now, during the travel, the power gets attenuated, because it has to travel through medium, power gets attenuated. And when the signal reaches the antenna, the receiver, its power is very low. Now you will be surprised to know the order of magnitude. It is on the order of 10 to the power minus 15 to minus 16 watts. 10 to the power minus 15 to minus 16 watts in case of GPS. In case of IRNSS, depending on what signal power is pumped, it will be lower, because it has to travel longer distance. Now, when the signal is picked up by the antenna, it also receives noise. So both signal and noise, and we clearly distinguish them. They are not the same. Signal carries useful information, whereas noise is unwanted, automatically generated during the propagation and during reception. So both signal and noise are received by the antenna, and signal power is so weak that at this point signal is actually below the noise. Meaning, if you plot the analog signal at this point, you will not be able to identify it. You will just see some noisy pattern, because signal power is lower than that of the noise power. Okay. Noise power itself is low, signal power is even lower. Now, such low power signals and signals cannot be processed by the receiver components. So the first thing that the front end does, it amplifies the signal plus noise power. At this point, it is not possible to distinguish the signal from noise. So whatever amplification it does applies to both signal plus noise. So it amplifies the signal plus noise power by about 10 to the power 10 times. Using some power amplifiers, it amplifies the signal plus noise by 10 to the power 10 times, which in logarithmic scale would be 100 dB. You just do 10 times 10 log 10 times log 10, 10 to the power 10. So that will give you 100 dB. Okay. So the first thing that the front end does, basically it distributes the work, it amplifies the signal power. Its primary job is to condition the received signal, okay, so that it can be processed by the subsequent components. The first thing is amplifying the signal power so that it can be processed by subsequent components. The second thing is narrowing down the signal bandwidth. Now see, when the antenna receives the signal, it has a certain bandwidth, okay, depending on the antenna design, it will have a certain bandwidth. The bandwidth also depends on what signals the receiver is supposed to process, okay, and what code and carrier the receiver is supposed to process. Typically for code, CA code, it will be tens of megahertz. Now, if the bandwidth is larger, you actually introduce more noise, but you do not want noise. So one way to eliminate noise is to narrow down the signal bandwidth. But how much will you narrow down? You cannot narrow down just like that, because then you will distort the signal. In a previous class, we talked about the null to null bandwidth. In case of the CA code, it is 2.046 megahertz. Now, a rule of thumb for the narrowed down bandwidth should be at least 2.5, more than 2 times the null to null bandwidth. Okay. If you try to narrow down the bandwidth further, you distort the signal. Now, we do not want to distort the signal to a significant extent. Then we lose important information. So here the trade-off is that eliminate noise, but at the same time do not distort the signal. So it has to be designed properly with the help of band pass filters. Okay. Next, now the carrier frequency is few gigahertz. We have seen that L1 is 1.5 gigahertz, L5 is about 1.175 gigahertz, then S is about 2.4 gigahertz. Sorry. So processing signals at the gigahertz level would require more computational resources. A clever alternative is to change the signal frequency from gigahertz to megahertz. Later, when we talk about the front end in more detail, we'll see mathematically how this can be done. Okay, so what we do is we shift the carrier frequency from gigahertz to some intermediate frequency in the megahertz. This process is called down conversion. Okay, so after down conversion, we just need to deal with the signal at the megahertz level, not at the gigahertz level, and we can get comparable performance with less resources. Now, for subsequent components, we require digital signals, but at this point, we have analog signals. So the last thing that the front end does is it digitizes the signal. It converts the signal from analog form to digital form. So after the front end, we basically deal with the signal in the digital domain. We have a bunch of samples to process. Okay. Later we'll see how the front end does this in a more detail. The next component is the baseband signal processor. So the job of the baseband signal processor is to generate the replica, code and carrier. So here you see some carrier, code and navigation data. Of course, they are not drawn to scale because the order of frequencies are different. This is the carrier, code and navigation data. All the three components are present in the incoming signal. Internally, the receiver also generates a replica of code and carrier. Okay. Of course, it has to be in digital domain now. So it generates samples of replica, code and carrier and multiplies the replicas with the incoming signal samples. Okay. and then adds the resulting samples over a time interval called coherent integration time. This is of the order of few milliseconds. This process is called correlation. We talked about the autocorrelation and cross-correlation properties of the CA code. There we defined the correlation with integration. So integration is basically summation in the digital domain. So the job is to generate the replica code and carrier, and then do the correlation with the incoming signal. And the outputs are fed to the subsequent block called the ranging processing. What does the ranging processor do? The primary job of the ranging processor is to find some signal parameters. In case of the carrier, it is the carrier frequency or carrier phase. In case of the code, it is the code phase. We defined code phase in a previous lecture. So the code phase, just like the carrier phase, within a cycle we can define the carrier phase from 0 to 2 pi. In case of code also there is a period. The pattern of the code plus minus 1 repeats after a certain interval called the code period. The code phase is defined from the beginning of the code period. So if this is the current point, the code phase would be the number of chips before the current chip and the fraction of the chip up to the current point. So we can express this in seconds or in chips. We already defined this. Again, it is not possible to do the same thing. So if you do not look at the previous lecture, you will not be able to follow things. So basically here in the ranging processor, we are interested in finding the carrier frequency of the incoming signal, okay? And we also want to find the code phase. Now it does this in two ways: acquisition and tracking. Acquisition is a one-time process. Okay, what it does, it finds coarse estimates of the carrier frequency and code phase. Now, why the carrier frequency? See, later when we'll see the mathematical model of the signal at the receiver level, we'll see that there is a Doppler. Because of the relative motion between the satellite and the receiver, the receive frequency will have a Doppler component, which is not known. The carrier frequency at the transmitter level is known, but the receive frequency has a Doppler component added, which is not known. And to track the carrier, to find the carrier, the incoming carrier, we need to find both. The carrier frequency is known, but the Doppler is not known. That's why the receiver tries to find the carrier frequency, which is the transmitted carrier plus Doppler. The acquisition block under ranging processor gives a coarse estimate of the carrier frequency and the code phase. This is just a one-time process. Okay. Now, when the acquisition is done successfully, we say that the signal or the satellite has been acquired, and also the replica that the baseband signal processor generates is aligned with the incoming code within a chip. But this is not sufficient, and one-time process is not enough. So this has to be done continuously, and that is done by the tracking block. Okay, so it continuously tracks the parameters, the carrier frequency, code phase. It can also estimate the carrier phase. Okay, so it does this continuously for each satellite. So what is the objective of doing that? If it can do it correctly, then the replica code and carrier will be aligned with the incoming code and carrier, and that is what we want. We want to align the replica code and carrier with the incoming signal. Now, when the receiver successfully does it, it is said that the tracking loop, so basically there is a feedback control loop here. The path is closed from ranging processors to baseband signal processor this way, and that's why you have two-way arrows here. Okay, so the tracking is performed using feedback control. So when it aligns the replica code and carrier with the incoming successfully, we say that the loop is locked. And when that happens, it is possible to get the navigation data. So you know that code, carrier, and navigation data. Navigation data contains important information about the satellite. You want the navigation data. So that demodulation would not be possible if the replica, code, and carrier are not aligned with the incoming. So when they are successfully aligned, then it is possible to retrieve the navigation data. And it is also possible to generate pseudo-range and pseudo-range rate measurements. So the objective of the ranging processor is to actually find the navigation data from the signal and generate pseudo-range and the pseudo-range rate. Pseudo-range rate is basically the time derivative of the pseudo-range measurements. And this would not be possible if the replica, carrier, and code are not aligned with the incoming. So the tracking loop continuously does it, and when it does it successfully, the navigation data is demodulated, obtained from the the signal, and at the same time the range and range rate measurements can also be generated. But don't worry about all these things. We'll later discuss again at a top level. Of course, we'll not go into too much detail, and there you will understand why this happens and how this happens. Okay. So this navigation data and the measurements, they are called navigation measurements, are fed to the final stage, which is the navigation processor. Navigation processor employs a filter. Generally, it is the weighted least squares filter or the extended column filter, and the filter operates on the navigation measurements and finally gives the user position estimate, velocity estimate, and the clock error, receiver clock error from the GNSS system. So these are the 6 blocks: antenna, front end, baseband signal processor, ranging processor, navigation processor, and all of them are driven by a receiver clock. Okay. Any question? Next, what we'll do is we'll take up each of these 6 blocks at a time and discuss them in more detail. The first one that we'll talk about is the receiver clock. Now we know that the receiver clock has 2 components: reference oscillator and synthesizer. The job of the synthesizer is to basically derive different frequency reference signals from the reference oscillator. Okay, using a suitable circuit, it is possible. We will not talk about the synthesizer. Instead, we will talk about only the reference oscillator, some important property of the oscillator and how it generates the reference signals. Okay. GNSS receiver uses a quartz crystal oscillator. Okay. Quartz is a mineral abundantly found in nature. It is made of silicon and oxygen. Okay. So typically it uses a quartz crystal oscillator to generate the reference signal. So basically the crystal oscillator, this is the notation used for the crystal oscillator. Okay, is used in a feedback control loop in the feedback path. And the feedback control loop has positive feedback. It is closed through positive feedback. Okay. In the forward path of the feedback control loop, there is a power amplifier. The job of the power amplifier is to amplify the input signal power. So whatever signal is fed to the amplifier, the power of the signal, we define signal power. So the power is amplified by the amplifier and then output. It is driven by a DC supply. Okay, it requires a DC power to operate the power amplifier. So, and in a reference oscillator, there is a positive feedback control loop, and the primary components are the power amplifier in the forward path and a quartz crystal oscillator in the feedback path. There are other circuit elements as well for further processing, but we have not shown them. We have just shown the primary components to understand the operating principle. Now, the quartz crystal has a piezoelectric property. So, when a voltage is applied to the electrodes of the crystal, its shape changes. When the voltage is removed, it restores its shape, and in the process it generates a low output voltage which is fed back to the power amplifier. And then the power amplifier amplifies it further and sends it back to the quartz crystal. Now the question is how this positive feedback control loop generates a sustained oscillation. The reference signal will be either square wave, repetitive square wave, or sinusoidal signal. Whether it is square wave or sinusoidal signal, that can be determined by the additional circuit elements. We will not get into that. We just at this point note that we need oscillations at a precise frequency, and the oscillation has to be sustained. This is number one. Number two, how the loop will start. Now this is a self-starting circuit. So when the DC power is applied to the amplifier, even though there is no input signal, there will always be some internal noise because of the random vibration of the molecules. So that noise, internal noise, is picked up by the power amplifier when there is no input. Okay, and it is amplified. And that amplified noise is fed to the crystal. Okay. Now the crystal has a selective frequency property, meaning it can produce the output voltage over a narrow band of frequencies centered around a particular frequency. So whatever you feed to the crystal, the output voltage that you will get is always, depending on the type of crystal and some other properties, the output voltage will always have a narrow band of frequencies centered around a particular frequency. So it generates low output voltage over that narrow band of frequencies, and that is fed to the power amplifier. So earlier there was no signal, input signal. Now it got some input signal over a narrow band of frequencies centered at a particular frequency. So it will basically amplify that, and again this will be fed back to sent to the crystal. So this process repeats, and after some time what will happen is that the narrow band of frequencies centered at the particular frequency that the crystal generates is only sustained. All other frequencies die down. So because of the frequency selective property of the crystal, only a narrow band of frequencies centered at that particular frequency are sustained. Other frequencies die down. But how do you make sure that the oscillation that you get ultimately do not die down or do not grow with time? That is ensured by making sure that the loop gain is unity. So the A of G omega is the amplifier gain, the transfer function in the frequency domain, whereas beta of G omega is the transfer function of the quartz crystal. So to make sure that the oscillation is sustained, the loop gain is made unity. The loop gain is unity. So whatever amplification that you get from the power amplifier is actually attenuated by this crystal. As a result, the amplitude remains the same. The oscillation amplitude neither grows nor attenuates. It is sustained. Similarly, the phase is plus minus 2n pi. So there is no phase shift also. This way it is made sure that the oscillations are sustained. We get only a narrow band of frequencies for the oscillation centered at a particular frequency. That particular frequency is called the resonant frequency of the crystal. And it is actually determined by the shape, size, thickness and cut of the crystal. So depending on the shape, size, thickness and cut of the crystal, its resonant frequency is determined. So basically from this positive feedback control circuit, we get sustained oscillations over a narrow band of frequencies centered at the resonant frequency of the crystal. Okay, but how do we derive time? Now we know depending on the shape, size, thickness and cut of the crystal, what is the resonant frequency. So we expect oscillations to be at that frequency and it will be spread over a narrow band. That band is much smaller than the resonant frequency. So we can count the number of oscillations. For example, if the resonant frequency is say 1 megahertz, then we know that there will be 10 to the power 6 oscillations, 6 cycles in a second, right? So if we can have additional circuitry that measures or that counts the number of cycles, using that we can keep track of time, because when 10 to the power 6 cycles are over, we know 1 second has elapsed. Assuming that it is an ideal oscillator, there is no error, nothing. So this way, by counting the number of oscillations with the help of additional circuitry, we can keep track of time. Any question, anything that you did not understand, you will not find this discussion the way I am discussing anywhere, okay? So if you do not understand anything, ask me. Have you understood how the oscillations have been generated through positive feedback control? Nobody understood. Should I assume that nobody understood? So nobody understood this. Shall I repeat? At least you can say yes or no, right? Are you not following anything? You're not following anything? Are you following or not following? So you do not want to say that also? Are you there or not there? Tell me that first.
There,
Yes, ma'am.
So you are not following anything? That at least you can tell me, right, whether you are following or not.
Ma'am,
Yes.
actually we have a frequency multiplier and frequency division devices. So how it is different from you have just mentioned that
1
how it is
minute.
different from that?
Yes, say that again. Say that again.
Actually our system have 10.23 megahertz oscillator, main oscillator.
Yes. Yes.
So we use frequency multiplier or frequency
Yes.
division. We have two things. We can multiply it.
That is
So
the job of the synthesizer. We are not discussing the synthesizer. We are discussing how the 10.23 megahertz signal is generated. In fact, in case of the reference oscillator, it is 10 megahertz. It is not 10.23 or okay. The oscillator will generate signal depending on the crystal. The synthesizer has to derive specific frequency signals as needed for different blocks. Okay? No, but are you following what I am saying? How that positive feedback control generates oscillations? If you are not following, you should stop me and ask, right? So should I assume that you have not followed anything?
yes, ma'am, I didn't get that.
Which one you did not get?
That feedback.
Ajita, you also did not understand? Shujit?
not so clear, ma'am.
Then you should ask me, right? If something is not clear, if I ask question, you will not be able to answer that, right? Which part is not clear? How the oscillation is generated?
Yes, ma'am. The last.
Huh? Which one?
The last part which you have taught just now, the how it is generated from the quartz crystal.
So see, the quartz has a frequency selective property. Whatever input you feed, it will generate output. This is a property of the piezoelectric crystal. It will generate output voltage. You can think of a sinusoidal signal spread over a narrow band and centered at a particular frequency. You just think of a sinusoidal signal at a particular frequency. That you understand, right?
Yes, ma'am.
And then you just think of a narrow band around that particular frequency. So that is what the crystal will generate always, irrespective of what you feed to the crystal. It's a property of the piezoelectric crystal. Okay? And that only you are feeding back to the power amplifier. So what will the power amplifier do? Power amplifier now has an input signal, so it will amplify that only, right? And that amplified signal is again sent to the crystal. So basically what you are doing, you are actually sustaining one particular frequency and a band around that frequency, right? Because the filter, the crystal here outputs only at that particular band. This you understand? Other frequencies will not be sustained, right? Although initially noise was generated, you can think of it as white noise. So it is spread over all the frequency band. But the crystal will not allow that. It only outputs voltage at a particular frequency and a band around that, narrow band around that. That is only fed. Power amplifier will basically amplify that, and this will be again sent to the crystal. So these only will be sustained, correct? Other frequencies will not be sustained. Is this clear now?
Okay, ma'am.
Yes, ma'am.
Now, how do you make sure that the oscillations do not grow or attenuate? This can be ensured by making sure the loop gain is unity. So whatever attenuation you get here, so you feed some voltage. The crystal will not generate the voltage at the same level. It will generate some low voltage. So basically it attenuates it. Power amplifier amplifies it. So whatever you attenuate is amplified by the power amplifier. That's why this loop gain is unity. You attenuate it, low output voltage, it is amplified, you get the same thing. Whatever you had earlier, the same thing will be retained because the loop gain is unity. So at this point, if you see, it will remain the same because this attenuates it, but it amplifies it by the same level. So it will remain the same. You just think of some sinusoidal signal at some amplitude. At this point, it is attenuated, and then the amplifier will amplify it by the same amount. So you just get the same thing as before, right? By ensuring that the loop gain is unity, you can sustain the oscillation. It does not change in amplitude, neither it grows nor it attenuates. Is this clear now? How by making the loop gain unity, and also the phase is 2 and pi. There is no phase shift as you go around. So say you cut at this point. So this is one point, this is another point. How much will be the phase shift? Phase shift is 2 and pi. There is no phase shift, right? Had there been a phase shift, then you would have got over different time instance, you would have got different signals. Here there is no phase shift. So you will not get different signals. This is how you sustain the oscillation. Is this clear now? You just cut it at some point. So say you feed some signal. Signal goes through quartz crystal, signal goes through power amplifier. How much will be the phase shift at this point? 0. Plus minus 2 and pi is equivalent to 0. You do not have any phase shift. So this way you make sure the same thing repeats. That's why I say the oscillations are sustained. Ajita, is this clear now?
Yes, ma'am.
Okay, we'll continue tomorrow.